Okay, I'd like to welcome everybody. Thank you for coming. I know a few people may join as we go ahead, and so I appreciate your patience with that. This is the first of 3 scheduled identical orientation sessions today for the 2023 virtual CompuCell multiscale modeling workshop. Today, we're going to just introduce a few basic concepts and get people started, I hope. The slide deck that you're seeing today will be available online in the student materials folder. We've created a Slack channel for people to use. This meeting itself will be live streamed on YouTube and made available for future viewing if you need that. And as always, it's a good time to either register for nanoHub if you haven't done that already, or install CompuCell3D on your desktop if you're going to run it locally. As always, we're grateful to our funding from the National Institutes of Health and the National Science Foundation for this work. Today, we're going to talk a little bit about the course logistics, some things you might want to do to plan for the course. We'll talk about the hackathon. I hope many of you will decide to participate in the hackathon. We will talk about resources, and we'll do a quick exercise using CompuCell together. We have about 150 people registered for this class. That's a very large number. We'll do our best to support everyone, but please be patient. Today, online, we have Hayden Fennell and Pedro Del Castel, who will be available to help people with questions. And I've created 2 breakout rooms that can be used if you need more intensive help. Hayden and Pedro, I don't know if you want to introduce yourselves.
Yes, my name is Pedro Castel. I'm from Brazil. I participate with James in the group of CompuCell3D, developing demos, simulations, organizing the workshop. And I am a student at Universidade Federal do Rio Grande do Sul, a Brazilian university. And yes, that's my introduction. I am currently a master's student.
Thank you, Hayden.
Hello, everyone. I'm Hayden Fennell. I'm a postdoc with the Glazier group and the sort of orchestrator of the workshop this year. So if you have any questions about logistics as we move forward, or if you need help with finding any resources or anything like that, please don't hesitate to contact me.
Okay. And again, we will post the link for the YouTube live stream in case some people internationally may have trouble staying in the Zoom. So if you need to watch this through YouTube instead of Zoom, it'll be possible. The problem with that, of course, is it'll be more difficult to ask questions, but you can use the Slack for that purpose if you need to. Again, we welcome everyone here, and we'll get started. So the key things that we are going to be trying to do today are understand how to model, that is, how to build computer simulations of fundamental biological processes. Those questions could be how organisms develop, how they maintain themselves, because organisms don't just stay the way they are, they have to actively maintain themselves, how maintenance fails in what are called developmental diseases, the classic developmental disease being cancer, but there are many of them. What happens during infection, how pathogens spread in the body and how the immune system eliminates pathogens, and the damage that the immune system can cause to the body, and also how the body recovers after damage. Toxicology, how chemicals can cause damage to organ systems in the body, and how that works, how the body recovers. And then potentially how we can use computation to optimize control of diseases or to design bioengineered systems that did not exist in nature. All of these involve complex interactions of biological control, typically gene regulatory networks, metabolic networks, and signaling networks with the complex biomechanics that occur at the cell and tissue level. And really, the kind of modeling we're doing is trying to explore that emergent phenomena that lead to the complexity of life. When we think about biological organization, it's highly multi-scale. We have processes occurring at every scale from single molecules up to the whole organism. And if we really think about ecosystems, of course, then we have processes on larger scales as well. We have to think about how to do modeling. We can't model everything at once. And biology is characterized by what we would call emergent phenomena. Interactions within and between scales lead to much more complexity than you would expect from the components individually. What we call virtual tissues, which is what we'll be talking about in this class, focus on how cells interact with each other, how cells are controlled, and how that control leads to large-scale organization in a tissue. There are many kinds of examples of this. These are all simulations that were done with CompuCell3D at various times. Some of these are quite old, from 2009. Some of them are a little bit more modern, but they illustrate the variety of problems that you can address with CompuCell and other modeling systems of this kind. In the top right, we have a simulation of a growing tumor. As the tumor grows, the center of the tumor becomes hypoxic. It doesn't have enough oxygen. It sends out chemical signals, vascular endothelial growth factor, that induce growth of blood vessels, here in red, and those blood vessels then supply additional nutrient and oxygen to the tumor, which then grows more rapidly. In the top left was a study which was related to drug development, looking at a disease called polycystic kidney disease. In polycystic kidney disease, you get improper growth in the kidneys. It never becomes cancerous, so it's not a cancer, but it is a proliferative disease. And the questions that were being asked were, what were the mechanisms that were controlling that improper proliferation so that we could try to develop chemical therapies for the disease, because at the moment it's only treatable by kidney transplant. At the bottom left was a study in personalized medicine, trying to understand how photocoagulation therapy that is used for treating diabetic retinopathy could be optimized so that it was more effective and caused less damage to the retina being treated. Bottom right is another retinal simulation. In this case, the retinal disease is choroidal neovascularization. It's a disease in which blood vessels invade the retina where they shouldn't be and chew it up and eventually destroy it. Diabetic retinopathy and retinal neovascularization together are some of the main causes of blindness in adults in the developed world, and they're both quite difficult to treat. This kind of modeling has also been used in a toxicological context. These are studies by the U.S. Environmental Protection Agency, trying to understand how particular chemicals in the environment can lead to disruption of development of embryos. In the first study, they were looking at disruption of blood vessel development in embryology. The second study was looking at how estrogen mimics, hormones, and hormone mimics in the environment can lead to a urogenital development. There's been a lot of concern about estrogen mimics causing improper genital development in animals and humans. And this was a study trying to understand that. The third one was a study of the development of the palate, the roof of the mouth. Cleft palate is not a very common birth defect, but it occurs. And they're trying to understand how environmental perturbations could contribute to the frequency of that disease. There's been a fair amount of work done with multi-scale modeling, trying to understand how viruses invade the body and how the immune system responds to those viruses. This is a simulation that was done actually initially as a student project, looking at a patch of lung tissue. In this, we simulate the infection of a single cell in the lung. That infection spreads. You see virus load, the response of the lung, which is the cytokine level, the immune signals in the lung, and then the appearance of immune cells that come in and try to eliminate the infected cells. And this one is actually one that you can run online if you like. So these are a couple of examples of the different kinds of things that you can do with this kind of modeling. We hope during the workshop and during the hackathon that we'll learn about what you want to do and understand that better. And we'll have some orientation sessions for the hackathon, which you can use to tell us about your interests so that we can help you develop the models that you're interested in. We hope by the end of the workshop, you're going to be able to look at a biological problem, identify what kinds of questions you could ask and answer using simulations of the kind that we develop, analyze the components of the biological system that you work on and their interactions, and then use those analyses to build a computer simulation that works, and then implement that simulation, analyze the results, and determine biologically meaningful outcomes. These are not easy things to do. None of these are easy things to do. And so don't be discouraged if it takes time and practice to be able to do it. Nobody comes into this knowing how to do everything you need to do. And while you don't need a lot of depth in any single area, you do need to master a lot of things at the same time. Let's just talk a little bit about course logistics. We don't have yet the final Zoom link for the workshop and the hackathon. Those will be set up in the next few weeks, and we'll distribute them. For the orientation sessions today and the hackathon organization, we'll use the Zoom link that people are in today. There is a document for hackathon preparation. Hayden will reshare the link for that document now, and there's going to be a hackathon channel for discussion. Again, I encourage people, certainly not required to participate in the hackathon, but I hope people will. It's been quite productive over the years. It's a lot of fun. It's a lot of work. It's intensive, but it's also an opportunity to work in teams across the world. Sometimes people come together with a team that they already have. You have a bunch of students in your same university, for example, but we've also had teams where you had one person from Australia, two people from India, somebody from the Netherlands, and somebody from the US working together. And it's wonderful to see that kind of international collaboration happening through Zoom in these hackathons. So we encourage you to participate. Zoom logistics, we won't have screen sharing turned on, but you should be able to talk if you need to. If for some reason you can't unmute when you need to be able to unmute, raise your hand in the chat and we'll do our best to make things work. You can use the go faster, go slower buttons in the participant screen to let us know how things are going. When we do exercises in the main class, we'll do quick polls to ask you if you need more time. Sometimes you won't be able to get through the whole exercise in the amount of time we have, but we hope that you'll be able to get through most of it. All of the exercises and results will be made available online, and all of the videos and PowerPoints will be available so that if something happens, you can't watch things in real time, you can catch up. As I said before, everything is live streamed on YouTube and made available afterwards. This year, we have a great group of instructors. I'm James Glazier from Indiana University. We'll have Gilberto Tomas from Brazil helping us teach. He's taught for many years. You've met Pedro, who is going to be teaching us, helping as well. Giulio Belmonte from North Carolina State University will be helping and teaching. Jim Sluka, also from IUB, senior scientist. Joshua Ponte Serrano, he's listed here as IUB, Actually, he's at the National Institutes of Health now. We need to update the reference for him. Priyam Adhyapok from Duke University, TJ Sego from University of Florida, and Hayden Fennell, who is our course coordinator, also from IUB. And so we have a great team available to support you here. The daily course schedule will have a brief opportunity for questions and comments just before the class starts. The classes will always start at 10 a.m. Eastern Daylight Time. I realize that that's not much fun if you're in India or China, but it's the time that works the best for the world as a whole. We're sorry, and we appreciate people who stay up all night to participate. We know it's not so easy. This year, we're going to be changing the course format a little bit from last year. Last year, it was very intense. People requested that we add days to the course and reduce the intensity a little bit. So each day is going to have the same rhythm. There will be 3 modules. Each module will be an hour and a half. That will consist of about half lectures and about a little more than half exercises, hands-on exercises. We'll have breaks between the modules. And then at the end of the day, there'll be self-guided, more deep exercises with this opportunity for help from the educational team. And that's the new innovation that we're going to have. And then we'll have a little wrap up where people can ask questions at the end. And so we hope that this format will be effective, a little bit more time for people to catch up and think about the things that we're doing rather than having 4 modules of lecture every day. That's pretty intense. We'll have completion polls at the end of every exercise, and at the end of every module, we'll ask you for your opinion. How did it work? What could we do better? And we'd very much appreciate your feedback on how we can improve. Every year, we take the feedback from students and participants very seriously and do our best to incorporate that in the following year. This year, we're going to have a 2-week format. The week 1 will cover the basics of CompuCell, the various things that you can do in CompuCell, how you control cells, how you build chemical fields, how you have cells and chemical fields interact, how you apply forces to cells. And then in week 2, we'll do more advanced work. We'll talk about how to implement and integrate biochemical networks into your models. We'll talk about how to build compartmental cells, which allow you to represent things like epithelia and crawling cells. And then we're going to have more advanced topics on materials, network execution and cluster execution of simulations. And we're going to have breakout sessions where we're going to cover advanced simulations, some of the ones that you saw pictures of at the beginning of this lecture. Then we're going to have that weekend hackathon where we hope people can get together and build preliminary models of the systems that they're interested in. This class it's not a graded class. You're not registered in a university for it. People are here because they want to be and because they want to learn. But to get the most out of it, it does help to have some advanced preparation. And we will do our best to be available to you to answer your questions and to support you technically during the workshop. So let's talk a little bit about background and reading. Nobody comes to this class unless they've been doing this kind of modeling directly, knowing all of the things that you need. And so you don't need a great deal of depth on any of these things, but you do need to have some level of understanding of all of them, at least by the end of the class. And so it's worth thinking about the things that you need to be able to do. Some of them are pretty straightforward. You're going to need to do a little bit of Python programming. It's helpful to have a little bit of mathematics, a little bit of physics. And since we're modeling biology, you need to have some interest in biology. However, there's one thing here, which is actually the first one, which is called principles of modeling. So sometimes called quantitative thinking or computational thinking. And that's not talked about so much. And that really is a question about how you ask questions, how you say, is this problem that I'm interested in something that a model or simulation can help with? How do I analyze a complex real world system into components that can be modeled? How do I map their behaviors onto computational and mathematical ideas? And how do I understand the limits and meaning of the models that I develop? This is a set of ideas that sometimes are taught in engineering, but are not taught so often in the context of science. And I think that we take it for granted that people know how to do this, and it's not so easy. And so I hope that people will learn during the next 2 months till the end of the course more about how to think about things from a modeling perspective. Many people come to this class with a pure mathematics background, so they haven't encountered biological problems so much. We have many experimental biologists who've never done any computing or mathematics. We've had surgeons take this class. We've had high school students take this class. We've had retired professors take this class. We've had physicists take this class. And so people come from all sorts of backgrounds, and we work together and we try to team up so that we can learn from each other and understand each other's thinking. When we come to Python programming, you don't need very much, but you do need a little bit. We'll have a day of Python review for people who either don't know Python or want a little bit of a review. You're not going to be using very advanced Python in this class, but there are some basic concepts that you'll need. You need to know what Python indentation is. People often find that confusing when they first get started. Python uses indentation rather than parentheses to define block structures. You'll need to know how loops work in Python, how logic and conditionals work, the various kinds of Python objects. In particular, Python has concepts of lists of things, dictionaries of things, which is a very important Python concept that's not present in all languages, and that's basic to the way CompuCell is controlled. Classes, at least a little bit, scoping and inheritance, and how you define things like methods and functions. You don't need a lot of Python, but it's very important that you're comfortable with the basics. And so we strongly encourage people to learn a little bit of Python beforehand if you haven't done it before. If you have any insecurities at all, we should definitely have you take the Python boot camp that first day. So that's available to you. There are great online resources available for people to learn Python, which are free. I particularly like the Rosalind package for learning Python. Maybe Hayden could put the link for that in the chat, but there are many others. I would recommend, if you haven't used Python before, that you spend at least a day or two learning the basics beforehand. There's a Python cheat sheet which we've handed out that has the basic Python syntax in it. Playing with that a little bit would be very helpful to people. Maybe we can just use it. We could test out how people do with Zoom. If we could just get a show of hands, maybe using your reaction buttons in Zoom. How many people in the room have done some Python programming before? Okay, so it looks like about half of the people have done it before, maybe a little bit more. Again, don't be intimidated. The amount of Python you need is not very large, but it will be very helpful if you have a little bit of experience with it before the class. We will go slowly. We will introduce every Python step and discuss it as we develop it. So you can definitely learn it on the fly, but it'll be just a little bit faster and easier if you've done a little bit before. biology. This is really a class about biology, although this modeling methodology can be used also to model materials. You don't need to know a lot of molecular biology. In fact, there's almost no molecular biology in this course. This course is about cell, tissue, developmental biology, cancer biology, systems biology. And so the primary things that we have in our simulations are cells. And so understanding a little bit about what cells are and what they do is very helpful. You want to understand how cells move, how tissues reorganize. And so it's useful to understand how cells generate forces. How do they respond to forces? How are tissues constructed? What are the principles of organization of biological tissues? There's some basic biological concepts like mesenchymal and epithelial tissues. Mesenchyme are three-dimensional tissues. Epithelial are sheets of cells. It's very important to understand the basics of how those work. Cells are oriented. They have polarity and planar polarity. Those are concepts that we'll introduce, but it's good to be familiar with the basics of those as well. What is the extracellular environment and what is extracellular matrix? What are biological networks? Classically, metabolic networks that produce the components of a cell and its energy. Regulatory networks that control the state of the cell, turn genes on and off, and signaling networks that allow the cell to respond to its environment and signal to its environment. What are chemical reactions? What are regulatory interactions? How do networks control cell behaviors? When we're talking about networks, are there basic motifs? Are there basic patterns of network that we can understand? In tissues, blood vessels are a particular organizing feature. How do they work? And more generally, how do biologists think about complex problems? How do they represent information? How do we take a picture like the one on the right and turn it into a simulation? How do we understand it? We will try to minimize the amount of mathematics and physics that you need in this class. However, these are a lot of physics and mathematics concepts that can be quite helpful. They're not essential, but some of them are very helpful. The very basic concept of a spring and an ideal gas law, the idea of a constraint, are very important and useful to understand. Diffusion is a fundamental process in biology. What is a diffusion length? What is a diffusion time? That is, how far does a chemical get when it diffuses? And how long does it take to get there? If I push or pull on something, how fast does it move? That's called the force-velocity relation. How does it change its shape? It's called a constitutive relation. The underlying mathematics of CompuCell is something called GGH or cellular Potts model. You don't absolutely need to know how that works, but it helps you understand, especially when things don't go right in your simulation. It's useful to know a little bit about how that works. Statistical mechanics, if you're interested in really the underlying back end of CompuCell. How fluctuations work in biology and in physics. And more generally, the fundamentals of biophysics, which tend to be related to what's called statistical mechanics. Although the single thing that you're most likely to need is to understand the diffusion equation. In terms of mathematics, again, we'll try to minimize the amount of math we do in the class. But if you can understand some basics about what are called dynamical systems, how rate laws work, chemical reaction laws work, that could be very helpful. There's a course that's given every summer by our collaborator, Herbert Sauro, which focuses on network modeling. Many people who take this course also take Herbert's course. That's useful, but not required here. Concept of stability, steady states and fixed points is useful, and how you do things like sensitivity analysis are useful. Again, these aren't requirements, and many people may have run into some of these concepts, and not some people may not. As I say, there are a lot of different things. We don't need any single thing at a very high level, but it's a lot of different things to be aware of. And so depending on where you come from and what your background is, you might want to review one or more of these topics a little bit before the main course. There's a nice paper that was written by a group of Canadian students a few years ago called 10 Simple Rules for Your Mathematical Model. That is an introduction not really to multi-scale modeling, agent-based modeling, more to ODE modeling, but has some great ideas in it, a very useful set of ideas. Recommend that a lot. We mentioned the Rosalind exercises for learning Python. There's some good introductory Python texts online and available. For network modeling, we'll be using the Tellurium package. There's a great set of demonstrations on the Tellurium website. Maybe we should post that link in the chat for people, and we'll have a handout about that as well. For mathematics, you again don't need a lot of detail. There's a wonderful textbook called Essential Mathematical Biology that I like a lot for people getting started. Wikipedia has really good articles on the basics of the mathematics as well. For biology, quad biology, probably the best place to start is Gilbert's textbook, Developmental Biology. You can get older editions of that textbook online for $2 or $3. You don't need the most recent edition, which has a lot of mathematical detail in it. The old editions have the basic ideas just fine. If you want to dig into the biophysics, there is a wonderful introductory textbook by Phil Nelson, Physical Models of Living Systems, which gives you some background. If you really want to get in more deeply, Physical Biology of the Cell is a wonderful textbook. I've taught out of it many years for graduate students, but it's pretty advanced. And you certainly won't need all of that material here. If you want the background on how CompuCell works, the guts of CompuCell, we have a paper from a number of years ago, which will be shared in the chat and is available in student materials. If you find any online materials or other materials that you think are really good educational resources covering any of these topics, we strongly encourage you to let us know, and we'll add them to the resources and distribute them to everyone online. For workshop resources, there is the CompuCell website. We hope people either have been able to download or get onto nanoHub already. There are the online manuals. There is a old quick start guide, which is a bit out of date, but still helpful. We have the Slack channel, of course, Google Drive, Tellurium manuals, and the quick start reference guides. I hope that this will be useful. If people find bugs, typos, errors, or omissions in the manuals, please do let us know. Absolutely, this is a small team project, and so there are mistakes and things that are missing or even out of date. And so if you find something that's not right or missing or needs additional clarification, please do let us know, and we will do our best to make things available to you and fix it. We depend on our users to feed that back to us about what can be improved, what's wrong. And so please don't hesitate to let us know when there's a problem. There is a Slack channel. I have to say I am not a Slack user, but Pedro and Hayden and the others are big Slack users. And we hope that people will be able to build community this way. We come from all over the world. We're online. The best resources in some ways that you have are the other participants in the class. And therefore, we strongly encourage people to work through the Slack to build teams, ask and answer questions, and work together to build understanding. This really is a collaborative effort. And if some people get excited and want to build core CompuCell code, we're happy to work with you on that as well. Again, we can repost all of these links. I know some people may have joined a little bit later, and I know one of the issues with Zoom is that if you join at Zoom, you can't see what was in the chat before you joined. And so if anybody needs these links reposted, type that in the chat and we'll repost any missing links. We have 3 quick reference guides. There is a Python cheat sheet. It's a couple of pages. You don't need all of the information in the Python cheat sheet, but it's useful to have it. Sorry. There is a CompuCell3D quick reference guide that's available online and is updated, but I strongly encourage you, if you can, to print out a copy of it and have it on your desk next to your computer so that you don't have to continually reference back and forth between the quick ref on your screen when you're working. It's very helpful to have a hard copy. There is a guide to Tellurium, which is the network modeling software that we use, which is also quite helpful and quite short. Those are things I would print out and have available. Something that's a little bit new, which we're still learning about, is that ChatGPT is a great source of information, and it can also help you write CompuCell code. It knows actually quite a bit about how CompuCell code works. Doesn't always work. Sometimes it gives things that don't work, or it'll say it can't do it. But if you're in doubt and you have a ChatGPT account, you can ask it to help you with CompuCell coding. And I strongly encourage people to use ChatGPT. If you have a biological question, a mathematical question, computational question, try ChatGPT or your favorite equivalent. I use ChatGPT now when I'm doing computer coding myself. I'll say, give me a Python program to do X, Y, or Z. And it usually will come up with something that's pretty good. Usually not the full answer, but it helps a lot. Instead of having to dig through the manuals or dig through Stack Overflow, ChatGPT helps a lot. So I encourage you to use it. Always be skeptical. It makes mistakes. So don't just take the answers as given, but do use it. It will make your life easier. So again, we have a couple of articles in the student materials folder. There's that 10 simple rules paper from those Canadians that I think is quite good. We have a book, the book chapter on the history and mechanics of the POTS model. And those I think are really helpful for people. I'll talk for a few minutes now about the hackathon. We really would love to have everyone participate in the hackathon. We realize not everyone has time, not everybody has ability or interest, but we encourage you to think about it. You don't have to have an idea. People with ideas are always looking for people to help out. And so we will have a series of hackathon teaming meetings in the next few weeks, and then during the workshop itself, trying to help people put together teams. The ideal team would be 3 to 6 members. Fewer than 3, you're really working on your own. It's hard. More than 6, it gets a bit hard to organize. So we strongly encourage people to try to get 3 to 6 people together. Diversity of background and interests is important. Ideal team might be 1 experimental biologist, 1 mathematician or computer scientist, and 1 modeler. However, it's fine if you have 3 modelers together, or 3 mathematicians together, or 5 experimentalists. We've had all sorts of things work. We're going to have the hackathon on August 12th and 13th. You can start on those projects before then, but that's the official hackathon date. We're going to have 2 hackathon teaming meetings. We're going to have a variety of hackathon organization documents and help people develop teams. During the hackathon itself, we'll have check-ins in the morning, in the noon, and the evening, so that people can help work together. And at the end, we'd like everyone to do an oral presentation and show off what they've gotten done. We'll be happy to support you after the hackathon. We actually had a team a few years ago that started a company based on what they did in the hackathon. So these things can happen. We've had plenty of people who've done PhD theses based on their hackathon work or published articles about it. So those are really a great opportunity to build international collaboration, get help getting started, and work together. If you want to do a hackathon, but you really don't have an idea of what to do, reproducing existing models of the kind that CompuCell develops, coming from other sources or even from old CompuCell, is a great way of learning. And so if you say you want to do a hackathon, but you don't have an idea for yourself, and you can't find a team from the pitches, we have a list of published models using other packages, Physicell, Morpheus, Simune, and so on, that we think would be great things to reproduce inside of CompuCell. And so if you're interested in that, we'll do our best to support you on that. There's going to be this Hack channel, Slack, I get that wrong, Hackathon Slack channel, that's shared in the chat. We have a Google Doc where you can post your hackathon ideas and start team building. We will have project pitches, and we'll ask you to pre-upload 3 slides maximum for your pitch when you go over those, so that we can show those to the teams. And if you want to have a list of ideas about existing models that you could reproduce or extend, we have a folder and materials for that. And are there any questions about the hackathon or any of the things that we've discussed so far? Now is a good time to put in the chat any questions that you might have. Okay. When you do the hackathon, we hope that you will come in having an idea of what you want to model and why. And the one thing that we may do is, if somebody comes in with a great idea that just doesn't fit CompuCell, we'll do our best to explain why that might not be the best choice. Sometimes people come in with very ambitious ideas. The hackathon is short. The best thing to do is to try to do something that's simple, that can get done in 48 hours. And that can be the basis of a more advanced or ambitious project. And so we will try to help people be effective so that your time is used efficiently during the hackathon. We'll do our best to support you during the hackathon. Again, if you want to participate in the hackathon, you will need some basic Python. It's going to be essential. And so if one way of sort of testing where you are with that would be in that Rosalind online Python training program. If you can complete exercises 1 through 5, your Python level is probably enough for that. It's fine to be a beginner and join a team. Don't be shy about it. Teams always need additional members. So now I want to talk a little bit about CompuCell. CompuCell is a program, a pair of programs really, that help you build and execute simulations. Twidit is a model editor. And what we'll find is that Twidit is very, very helpful in building simulations rapidly. In particular, it has what are called code snippets. It has templates for the things that you do most frequently. And so instead of having to remember how do I do something to every cell of a given type, those things are pre-available inside of Twidit. Player is an execution environment that allows you to run CompuCell simulations and also do some level of control of those simulations as they're running and to visualize them. We hope that everybody in the room has CompuCell installed, if locally, if you're planning on doing that, or a nanoHub account. May I ask people what fraction, if you can raise your hand if you're planning on running locally on your computer. Okay. If you're running locally, what fraction of you have CompuCell running on your computer now? Or maybe a better way to put it is, how many people want to run CompuCell locally and are having trouble getting it running locally? we'll do our best to help you with CompuCell install on local installation. But with 150 people, I can't promise that we'll be available in real time to help people all the time. And so if you're having trouble with a CompuCell local installation, please contact us as soon as possible, and we'll do our best to help out. How many people were planning on using nanoHub? And if you're using nanoHub, is there anyone who's had trouble registering for nanoHub who's planning to use it? So, okay, Wenceslaus, could I ask you then, please contact Pedro through the chat and let Pedro know what your problem is with nanoHub, and he may be able to help you get onto nanoHub. Everyone else is able to get into nanoHub who's planning to use it? Okay. If you're going to run CompuCell locally, there is a release page that you can get from CompuCell3D.org. There are downloads from Windows, Mac, and Linux, and those should send you to the SourceForge for downloads. The CompuCell installers have changed. They're now Conda-based. Sometimes you have to run them multiple times. Occasionally they're slow. Occasionally there are issues with them. I know that CompuCell doesn't always run on all of the latest Macs. And so if you're on the very newest Mac, there may be some issues. Please let us know, because we'll try to fix those things. The nanoHub execution may be a little bit slow and clunky, but it's available for people as a backup. We strongly don't encourage you to compile your own CompuCell unless you're very advanced. We're not going to be able to support people doing compilation during the workshop, although we're happy to do that offline in other situations. So you should find most of the downloads in SourceForge. And again, occasionally you may have installation security issues. You have to run the installers as an administrator, and you'll have to tell your software that it's okay to install CompuCell even though it's not a secure program. And very often people get a little bit confused doing that. If you have problems with it, reach out to us and we'll do our best to help. If you're running on nanoHub, we're going to go forward on that. I'm going to be showing you nanoHub today. I will say before we get started on this, that unfortunately nanoHub didn't update, and there's a glitch with the base release of CompuCell, which we're working on getting fixed. This just happened the other day. And so we're going to be doing a small workaround today, which is that we're going to be using the CompuCell deployment in the slime mold tool rather than the CompuCell CC3D base 4X, which is the normal one that we would use. And we very much hope that by the time we get to the workshop that this glitch will be fixed. But nanoHub is a third-party system. We don't control the releases, and so we're waiting for their tech people to fix the problem. But we'll today be able to use the slime mold version of CompuCell. And so we'll slow down and try to make sure everybody's okay using that. Okay, to go get into nanoHub, and I'd encourage people now to do this in real time. So if you are using your desktop CompuCell, you can launch Twit++. If you are using the nanoHub release, go to nanohub.org, hit login, and log in. And why don't people give me a thumbs up when they either have CompuCell Twit running desktop or when they're logged into nanoHub. I'll give people just a minute or two to do that. And while we're waiting, people should leave your thumbs up, because I need to be able to see everybody's thumbs up. So I get a sense of I don't want to go ahead until people are ready. While we're waiting, Please, if you have any questions about logistics, about the hackathon, about background material, please put them in the chat and we'll do our best to answer them. Yes, Hayden says, please put your questions in the general chat. If there's anything that you're asking, almost certainly everybody has the same question. And so don't be shy about saying, I don't know how to do this, or I can't do that, or where do I find this? If you want that help, other people will want it too. So please don't be shy about that. We all come to this class not knowing things. There are a lot of things I don't know about CompuCell and about biology. And so during the week, you will hear me very often say, I don't know. And so there's no shame in not knowing something. And we want to help each other. We've got a great group of people here. Our goal is to try to work together to learn together. Okay, does anybody need more time getting either CompuCell desktop or nanoHub running? Okay, let's go forward. So for people who are in nanoHub, okay, so if you're not able to install on desktop, please then use the nanoHub install. And reach out to Pedro for additional support offline, okay? So please, is everyone in nanoHub who needs to be? Okay, remember, depending on where you're coming from, you might sign in with Google. If you're in the US, you'd sign in with an affiliated institution, but you don't need to be in the US to use nanoHub. You can use it from anywhere in the world. Once you're in nanoHub, you will get to a dashboard screen. You can always click on the little nanoHub icon in the top left to get to your dashboard. Once you're there, you can click where it says logged in and click dashboard, and it'll pull up your information. Once you're there, you're going to have to find CompuCell. And let me actually do a new screen share so I can show this happening at the same time. So again, for nanoHub, to go to the dashboard, you can click here. Or you can go to menu. And let's see, they seem to have changed they've changed their menu since the last time I was here. Go to dashboard here. Okay. Let's see if it's going to behave for me. Occasionally we will have a Zoom issue with problems with nanoHub interacting with Zoom. Normally it's fine, but of course, when I'm trying to demonstrate it, it's going to misbehave. Let me see how I can do this. Hayden, do you have it running on your computer? That may be faster. Are people able to get it working for them? I think the issue is just the spacing. Yeah, there we go. It's just the size of the window. Okay. So let me go here. What I'd like people to do, if you're going to be doing the nanoHub, you go to all tools, you search on slime mold.
Two words, you need to add a space.
Thank you. There we are. Slime, we'll do it. You'll see CC3D slime mold simulation. You hit the heart to bookmark it so it's available to you. And now I'm going to launch it. And here I would hit launch CC3D slime mold simulation. I already have it running, so I'm going to hit open here. And then you'll see this. Okay. I'll give people a second to get that running. If anybody needs help for that, let me know. Once you have it running, you can hit the execute button. And you should see this screen. I realize for the people who are using desktop, you don't need to do all of this. So desktop people, please be patient. nanoHub people are people at this screen. Does anybody need help getting to that screen? Okay. Once it starts, and this is a little bit of an annoyance, you have to actually start the simulation. To do that, you go where it says simulation type. You pull down one kind of simulation. We can just select the first one, maze, and hit run. Okay, there's a question in the chat. Please demonstrate how to find it. Okay, let's do that again. So I'm going to go to my dashboard. I hit all tools here. And now I'm going to type the word slime. And it winds up, there's only one simulation with the word slime in it. So it'll pull up CC3D slime mold simulation. I click the little heart to bookmark it. And then I click this button here that says launch simulation. Okay, did that work for you? Great. Okay, let's come back to our simulation. And so you just do, once you've got things loaded, you're going to go to where it says simulation type, pull down and select any of them. We're not actually going to be using this simulation. Oh, it's a very beautiful simulation. I encourage people to play with it. But we're using this because we need to get the CompuCell running. And the main version is stuck at the moment. Okay. Once you're running in CompuCell, you have a series of buttons here at the top. You have a pause button that temporarily holds the simulation. You have a run button that runs the simulation. The circle button that looks like the old record icon on a cassette player single steps the simulation. And stop will actually stop the simulation, and you have to restart it from the beginning. And now that we have CompuCell running, whether it's desktop or on your nanoHub account, we can begin to run CompuCell simulations. If you are on nanoHub, the next thing you want to do is going to be using Twidit++. If you are on your desktop, you will launch Twidit++. So people probably have that already running if you're a desktop person. If you are in nanoHub, you are going to switch from player, which is what you see now, to Twidit. And the interface is slightly different in nanoHub and desktop. In nanoHub, you are going to use either the edit icon here, which starts Twidit, or under File, you can pull down and do Start Twidit++. So let's do that. I'm going to go to File. Well, I'll use this icon, the Twidit icon. It says Start Twidit++. I click there. And you'll see a new window that is the editor window. you'll see two tabs. At the bottom will be a tab which is called Player, and next to it, it'll say untitled.txt twidit++. If you're running desktop, these are separate applications. They're not going to be in a single tab, although they interact with each other. So is everybody able to get twidit++ going, whether desktop or nanoHub? I'll give people just a minute to get that going. I see one person says it's okay. Okay, see a lot of thumbs up. I'll try the poll. And what you'll see with these polls, these completion polls, the completion poll will ask you, do you need more time? And what I'd ask you to do with this completion poll is, if I say I'm waiting, don't answer it. When you're done, answer it. Only say I need more time if I'm about to go on to the next step. And the reason for this is a simple one. The poll doesn't allow you to change your answer. And so I have to relaunch the poll repeatedly if I'm going to find out whether you're done or not. So here people are saying they're done. I see 6 people, 7 people, 9 people say they're done. One person says they need more time. 2 people say they need more time. So we'll give people another couple of minutes. Somebody says need help. If you need help, please message Pedro and he will help. If you think it's something that's of general interest, problem for everybody else, please put it in the chat. Okay, there's a question about not showing the graphics window. Yes, I will show you how to configure a player in a little bit. If you want to try configuring player on your own while we're waiting, within slime mold, first, there's a resizing issue. So you'll want to adjust the bounding box of CompuCell to be a good size. You'll want to adjust the size of the simulation window inside of the bounding box using the full screen and size adjusts. And then where it says window, there's a very helpful button here, which I want everybody to learn. I'll talk about it a lot. This is not available on desktop on Macs. It works on Windows and it works on nanoHub, but it will not be available on desktop on Macs, which is under window, you see this button that says tile. Click that, and it should lay the screen out in a way that allows you to see everything. Why don't you try that out and see if that works? We'll go over this again. Riddle, we'll go over this again many times, but why don't you try that out now while we're waiting? Okay. Does anybody else need more time now? So everybody got the editor working. I'm going to relaunch the poll. Or if you want, you could just, if you need more time, raise your hand. That may be the easiest thing to do. Okay. I'm going to go forward then with this. Okay. For nanoHub, there are a couple of things. Sometimes the screen doesn't redraw properly. If that's the case, pull on the lower left-hand corner of the bounding box. So let me pull this forward again. Oops. Let me pull this forward again. I'm going to resize a little bit. The lower left-hand, sorry, I said lower left-hand corner, lower right-hand corner of the bounding box will force a redraw of the screen. You don't need that if you're running desktop. Okay. Now we're going to go to Twidit. Desktop, just go to your Twidit. Inside of nanoHub, there'll be a tab that says Twidit. We're going to go to Twidit. Okay. You can always resize as you like by pulling the right-hand bottom corner. You pull the left-hand bottom corner too, but it'll make it smaller. Okay. Whether you're in nanoHub or desktop now, we are going to create a new simulation. And we're going to do that by going to CC3D project and select new CC3D project. So I want everybody to follow along. And you'll pop up a window that will say CC3D Wizard. And you have, as a default, new simulation. We can give it a name like 3, I think, because I have a bunch of them. We don't need to probably put a number in it. You could type my first simulation. You're pretty free on names, except you have to be a little bit careful about a couple of things. No special characters in names. No spaces in names. And don't begin a name with a special character or a number. And the reason for this is that nanoHub runs on Linux, and Linux has certain restrictions on file names. So I hope everybody can follow along. New simulation. Simulation directory. If you're on a desktop machine, make sure that whatever you're pointing to here is a writable directory. Occasionally, especially on Macs and Linux, people will have that point to something they can't write to, and that will cause an error. In nanoHub, you need to be sure that you're pointing to your user directory. So click on Browse, select your name, and select Choose. Don't try to write to the root directory because you don't have write privileges. Does everybody get that working? Anybody having problems with that or questions? Okay. Is it okay to go on? Okay, I'm going to hit next. And now I'm going to configure my simulation. And I have the ability to change the size of the simulation. 256 by 256 by 1. Here, I'm going to make this a little bit smaller so we can see both things at the same time. 256 by 256 by 1. Whether we have periodic or no flux boundary conditions, we'll leave things as they are. Some of this other information we can change later on, but the defaults will work for us today. So we just say next. The next thing we have to do is to create some cells. And we're just going to create 2 types of cells. We create a cell by typing the name of the cell type and hitting add. Cell 1, cell 2. I want everybody to follow along and do that. Does anybody need help with that so far? People able to get to this screen? Okay. Anybody need help? Okay. Hit next. We're not going to use any chemical fields today. So we'll hit next, skip that. And then we're going to specify the cell properties and behaviors. And if anybody's an advanced programmer and wants to help me improve Wizard so it has more detail, I would love to work with you. So if somebody for a hackathon project wants to add some screens to Wizard to make it more detailed, and you're a good GUI programmer, let me know. Okay. Okay. For cell properties, we're going to select contact, growth, mitosis, and volume local flex. Contact, growth, mitosis, volume local flex. Has everybody got that? Hit next.
James, sorry to interrupt. Could you make
Yeah.
Giuliano a co-host real quick? I don't seem to have the privileges.
I will do that. Okay.
Thanks.
So Giuliano has joined us. He's also available to help people out. So if you have questions and Pedro's busy, Giuliano will be happy to work with you as well. Okay, you'll get a message called configuration complete. We'll hit finish. And you will now see a line that says CC3D simulation. We will double click on that. And now you will have the code generated for the simulation. This is actually the computer code, XML and Python, that will run that simulation. I can save the project by hitting the double floppy disk icon, a very out-of-date icon, or I can go to CC3D project, hit save project, or save as if I want to change the name. To run the simulation, if I'm on desktop, I can either go to the top here, right-click, and say Open in Player, or if this icon here is not grayed out, I can click there. In nanoHub, I'm going to go to here, top, New Simulation, right-click, and select Open in Player. Try that. It's going to give me a message, current simulation is still running. You want to stop it, and I hit yes. In nanoHub, I then have to switch the tab to see my new simulation. It's loaded but hasn't run yet. And I'm going to hit play, and that simulation will start running. As I mentioned, sometimes I have to joggle the corner of the simulation to get it to redraw properly, and you should see that. So I'll wait for everybody. How many people got this simulation to run? One. That's not doing so well. Okay, what do people need help with to get this to work? Do you want me to go over it again? To walk you through it again? Do you want to try it on your own? Tell me what we can do to help you out. Okay, repeat the process. All right, so I'll walk you through it first in the on the slides, and then I'll do it again. Step 1, launch the simulation wizard in Twitter. You do that by going to CC3D project and selecting new CC3D project. Step 2, type the name of the simulation and select the directory you can write into. Step 3, here we've done that. Hit next each time. Step 3. You'll see general simulation properties. We're not going to change them, so just hit next. Step 4, specifying cell types. You type a cell type name, no spaces, no special characters. Hit add. You'll do that twice. You'll create cell type 1 and cell type 2, or green cell, blue cell. And when you're done with that, hit next. Step 4, select cell properties. Step 4, skip chemical fields. Just hit next. Step 5, select cell properties. Those are contact, growth, mitosis, and volume local flex. So let me walk you through that again. Doesn't take too much time. New CC3D project. New simulation 4 this time. General simulation properties I keep. Cell type specification. Cell 1, add. Cell 2. Oh, I typed that wrong. Cell 2, add. Next. No chemical fields. Contact. Growth. Mitosis. Volume local flex. Next. Finish. Okay. Let me give people a poll to see how we're doing on this. Okay, if you need help, please reach out in the chat to either Giuliano or Pedro. There are breakout rooms available if people need.
James, we have a problem in the breakout room. I cannot share my screen there. And the participants also cannot share screens.
Okay, let me see if I can fix that. Try now.
Okay.
Okay. For people who have got things working, you could try running the simulation and seeing what it does. If I hit run, I will see cells grow, and I'll see them change type, and I'll see them divide. Let me try relaunching the poll, see where people are. Okay. For people who are saying they need more time, could you please put in the chat what is the issue that you're facing? Or just unmute and ask the question. Somebody says the screen update is slow. Is that on nanoHub or is that on a desktop application? Somebody says that they can't run. So what is happening when you can't run? What is the error that you're getting? After clicking finish, nothing comes. Select, it's on the screen here, contact, mitosis, growth, and volume local flex. So let me come back. You will be in the editor window when you're done. And it will be closed. You'll see something that looks like this, new simulation CC3D. Do people see that or not? Once you have it working once, it will get much easier. So it's better to spend the time now and make sure that it works. And once you've got it done once, it'll be easier. Yeah, you may very well have to run it as an administrator. Okay. Gulsame, what's happening for you? Shiva, you say it works. Gulsame, are you able to get it to work? You shouldn't have to start over. But it's fine. Only takes a minute to go over it again. Anyone else having problems? How about a thumbs up again for people who have it working? I appreciate the patience for people who have it working. I know getting started, it's always a little bit of some people get it working quickly, some not. There's no problem. You say there's an error. The error is when you're running it. Lampros. That's not an error I recognize. So that one you'll have to go to Pedro for. Anyone else? On model editor, what do I select? I'm not sure. I'm not sure I understand. Okay. So if things crash when you're trying to save the file, it means that the directory you're pointing to is not a writable directory. So at the very beginning, when you select the simulation directory, if you're on nanoHub, you have to point to your personal directory. If you're on a desktop machine, you have to make sure that the directory you set as simulation directory is one you have write privileges for. Yeah. It's trying to, it will crash if you try to write to a directory that you don't have write privileges to. Anybody else having issues? This is why we do the orientation. We want to get through these teething problems now if we can, so that people don't have them later on. Okay. I'm going to move ahead a little bit. Giuliano and Pedro will help people who are trying to get things working. The things that I'm going to talk about now are things we'll come back to and cover again. So don't worry too much if you're not able to follow right at this instant. Okay. So I want to talk a little bit about the nanoHub release. Again, you'll have two tabs in nanoHub. One of them will be your editor tab, and one of them will be the player tab. And so you'll switch back and forth between those as you write code and as you run it. As I mentioned, you're going to want to resize your screen to fit in your windows. And also, if there are redrawing errors in nanoHub, pull that bottom right corner and adjust the size, and that will redraw the screen. You can resize your window inside the screen for the CompuCell player window by pulling the right corner. And within the player window, you can adjust the size of the components. Again, you have your buttons here at the top. Play, which will run the simulation. Pause, which we'll use a lot, which will halt the simulation temporarily, but let you keep going later. Single step, which will advance the simulation by one time step. And stop, which will stop the simulation and force you to restart. And I don't recommend hitting stop unless you really want to. If I hit stop, you'll see one thing that will happen is that the simulation bounding box will get redrawn, and I'll have to resize my windows. One thing that's very useful, again, is if you have a screen that doesn't make sense, go to Window, Tile, and it will relay out the screen. Went back to the old simulation. I need to relaunch the simulation. The reason we updated CompuCell was because there was a bug in this version where when you rerun it, sometimes it will run not the current simulation, but the previous one. If you do that, you have to go to your Twit and relaunch the simulation that you had from before. I'm going to have to see what's happening here because I'm not. Did I manage? I may have crashed. I may have crashed player myself. Let's see. Yeah, looks like I've got. What happened? Looks like I managed to crash player. Player. Let's see if it works. No. Not going to work. If things crash on nanoHub, you can hit terminate and you can launch again. When we have the new version of CompuCell, you should not have these problems. Okay. File. Simulation type. Put it. Going to open the simulation I just wrote simulation 4, and now I'm going to launch it in player. Get back where we were. Sorry about that. Got ahead of myself. Let me do this again. Slime mold simulation. You can come back another time. Absolutely. I know we're over time, so I don't want to keep people too much. I do want to show you a couple of things. No, before we break. I have the slime mold simulation. I better not talk and type at the same time. I'm going to keep hitting the wrong button. I appreciate people's patience. Okay. I'm also not used to using this workaround. So it takes us a second. Okay, now I'm going to go back to Twit. I'm going to open the simulation I just defined. Now we're going to run that simulation. You should have this. This is where I wanted everybody to be. I hope the time it took me to relaunch it, you all were able to get this to work. Somebody said, what's the advantage of using nanoHub instead of the desktop machine? Well, nanoHub has some issues, as we saw, but the big advantage is you don't have to install anything to your local machine. So if you have an old computer, strange computer, you can run on nanoHub. Over the years, the problem has been that when we've had 100 people who need to install CompuCell at the same time, and 50 people have a problem with the installation, we don't have the number of people to support everyone getting the installs working. And so the nanoHub at least means that everybody is running the same thing and you'll have the same problems. Doesn't mean it'll be perfect, but everyone will have the same problems. Okay. Does everybody have the simulation working? And now you should be able to hit run and you'll see cells grow. And now we could actually begin to play. You can zoom in using the scroll bar on your mouse and see what's happening to the simulation. Let me talk just a second about CompuCell simulation, and then we'll break as we run over a little bit. If I look in the simulation, I will see that there are two main components. There will be something called XML script and something called new simulation for steppables. The first part contains the static specifications of the simulation. The second part contains the dynamic specifications. Let's look at the code together. You can switch what you see by selecting the tabs in Quit, or by double-clicking on the name in the navigation bar. If I look in the editor at the XML, I'll see that it begins with something that says CompuCell revision, metadata, how many computer processors you're using, for example, and then something that says POTS that specifies how big the simulation is. For example, the simulation is 256 by 256 by 1. The next thing I will see is a list of the cell types. We had to create the cell types. Here I see cell type ID 1 is cell 1, cell type ID 2 is 2. The next thing I will see is the behaviors of the cells that I've specified. I've said that the cells have a contact energy, and I'll see a block that specifies how sticky the cells are relative to each other. Those can be edited in the model editor while you're running the simulation. And the last thing I'll see is something called steppable type uniform initializer. That creates the initial conditions of the simulation. It draws the cells and creates the initial cells. It will create a square with different kinds of cells. And you could change these values and see what happens. I could make the simulation box smaller, and that will create fewer cells at the beginning. If I go to the Python, I'll see a bunch of boilerplate code at the beginning that I can ignore. I'll see an initialization for cell in self.cell list. You'll see that a lot over the next few weeks. That does something to every cell. And I'm setting the initial size of the cells. Cell target volume, cell lambda volume are the size of the cell and its compressibility. When I want the cells to grow, I set their volume to be bigger. And so see cell.target volume plus equals 1. That's the Python set something, increment something by 1. You could change the rate at which cells grow in the simulation, 0.5. Once the cells get to a given size, I want them to divide. Here, I use the Python concept of a list. I create an empty list. I look at the cell. If its volume is bigger than 50, I add it to the list and make it divide. I then run through the list of cells to divide, and I make them divide. And the last thing that happens is when cells divide, I have to say what happens to the daughter cells. And in this case, I have a function called update attributes that says each daughter cell gets half of the volume of the parent. And if the daughter cell is of type 1, the parent is of type, sorry, the parent was of type 1, the daughter is of type 2, and vice versa. So the types flip. Don't worry about that too much. We'll go over it in detail, but that's the level of sophistication of the coding that we're going to do for the next month. A few comments about preparing for the class and the hackathon. Again, try this out. There are some nice demos. There's steppable-based mitosis, angiogenesis, and delta notch, which are built-in demonstrations for CompuCell. Those are nice to run. There are a lot of CompuCell demos on nanoHub, like the slime mold that you can play with. Review core concepts that you might be unfamiliar with. And I'm going to do a quick survey now for those who are still around of the hackathon interests. And to see whether we can figure out how many people are interested in the hackathon. So please do answer the hackathon questions before we break. And I appreciate people's patience with the snafu about nanoHub. And we'll have that sorted for you before the next meeting. So please let us know about your thoughts about the hackathon. And also, if you're having any more questions or problems here. We'll try to get people to help. Giuliano, there's a question from Shiva. Could you try to address that?
If it was made while I was at the bake route, I can't see the question.
Okay.
Yes,
So
I cannot see the question as well.
I've contacted Shiva already, James. I'm going to follow up with her after the meeting.
anything else that people want to cover before we break for today? I realize there's always some teething issues at the beginning of this. Once you've got it working once, you'll find that it is a lot easier to use. Please do fill out the hackathon poll that's active now. Again, you can always change your mind. If you say no now, you can decide to do it later. If you say yes now, you can decide not to do it. This is just to give us a sense of about how many people would be interested in what kind of support you might want. Again, it's just fine if you don't have a team, you don't have an idea. We'll help teams build, we'll help people find ideas. Looks like a lot of people would like help building a team. Somebody says, could you use CFD to cell growth and division for hackathon? That's something we should probably talk about a little bit offline. So you have a particular computational fluid dynamics code you want to integrate with CompuCell? Is that the idea? Or you want to use CompuCell to do CFD? Those are slightly different things. They're both possible. They're not trivial things to do. They're both fairly demanding, but they're definitely possible. So that's an interesting question. So let's set up a Zoom to talk about that together. Okay, any other questions or comments before we break? I appreciate your patience. I know at the beginning of this sometimes can be a little bit frustrating, but our goal is to get through all the frustrations now so that when we get to the workshop, everybody is set up and everything works smoothly. Thanks very much. Any other biofilm project templates? That's a good question. So we have a published biofilm model, which I don't believe is implemented in the current CompuCell. It would be good to have that as a demo. So we should probably at least replicate that old biofilm paper. And then we
also
go ahead.
Aniqua did one a few years ago before we were using nanoHub. And I think that's for CompuCell4X.
Okay, so if you can see if we can find that, that would be fine. But let's set up a meeting to find out what you want to do in more detail. Biofilms definitely are a good topic for CompuCell. Yes, absolutely. Anybody else? Any other questions? No, well, thank you for joining today. If this went by too fast or was confusing, you're welcome to come back at noon in 2 hours or an hour now, or at 6. I know that's not such a good time zone for many people, but we'll do our best to work everybody through and make sure that everybody's up to speed and we get things working. Okay, thanks everyone. Bye.